Hey guys, this is ultimately the same information from the PowerPoint that is on It's Learning for entropy and reaction favorability, but sometimes you might just want to see it in note form or hear me discussing it. So this is here if you prefer videos over the PowerPoint. So today I want to be sure that you leave class understanding what entropy is and when a reaction is favorable, when a chemical reaction or a physical process is favorable to happen. Okay, so when you have a physical change or chemical reaction that is favorable, then it doesn't require outside help or intervention once it has begun. Okay. Many processes require a little bit of energy input at the beginning, but then they just keep going and going until they're finished. Okay, so for example, like you have to strike a match, right? You have to put in a little bit of energy to start that fire, but that exothermic reaction will burn much longer and with much more energy release than you put in. Okay, reactions usually aren't favorable in both directions. So almost all chemical reactions can go one way and then back the other. They can go in opposite directions, but usually only one direction is favorable. For example, this is rusting, the chemical reaction for rusting. Okay, and you notice that its heat of reaction, or that enthalpy change, is negative 1625 kilojoules. Okay, that's an exothermic reaction, and this will just continue until the limiting reactant is used up, okay, without any input of energy. The opposite direction of rusting, rust turning into iron and oxygen, is an endothermic reaction, a positive 1625 absorption of energy, and this is a non-favorable reaction. So even though this is the same chemical reaction, just going in the reverse direction, only one is favorable. Okay. Most reactions in nature are exothermic, and I've mentioned that a few times in class. And this is because they are energetically favored, right? The products, after that energy release, the products are more stable because they have lower energy, okay? But this isn't true 100% of the time. Some endothermic reactions can be favorable, okay? So we can't just assume that if it's exothermic, it's favorable, okay? So if endothermic, a positive entropy or enthalpy, could be favorable, we need another way to decide if something is favorable. We need something other than enthalpy to decide favorability. That is where our friend entropy comes in. Okay? Enthalpy is H, entropy is S. And these are the units. Okay? It's moles per Kelvin instead of grams. And what entropy is, it's not a measure of heat in the system, it's a measure of disorder, of how random your particles are behaving. Okay, so this gas would be high entropy. It's very disordered, they're really random, bouncing all around, all over the place. This would be a particle diagram of a solid. This is low entropy. Okay, it's very ordered. Another way to think about entropy is that it's a measure of all possible ways energy can be distributed. Okay? To predict the entropy in the system, it's the exact same formula as enthalpy. Okay? So you would need the entropy of the products and subtract the entropy of the reactants to get that change in entropy, the change in the amount of disorder. If you have a positive change in entropy, a positive delta S, then you've increased your entropy and you've increased your disorder. Your particles are all over the place now. If you have a decrease in entropy, a negative delta S, that means you have gotten more order to your system. Okay, so if you had to assign a positive or a negative to these, I would give this one a positive S and this one a negative S. Okay, but really this is a change in entropy. You can't call just one thing a positive change in entropy, but just for a visual. Increasing your entropy would be a positive delta S. So these are some things, some ways that you can increase the entropy, increase that disorder, increase the craziness. Okay, anything you do to increase the particle movement will increase entropy. Okay, so if you give it more volume, if you give those particles more space to bounce around, if you add energy or temperature, right? Temperature is just a measure of the kinetic energy. If you add particles, okay, and that comes in the form of moles or grams. If you increase their state of matter, right? You know that solid particles look like this. Liquids are a little bit more spread out, and gas is all over the place. So when you go from solid to liquid to gas, you are increasing the disorder and the entropy. And anytime you make a solution, anytime you dissolve something into a solution, especially a gas, that will increase the entropy. Okay, so at this point is a good place to stop and work page 6, numbers 1 through 5, and then come back to the video that I'm going to post next and see and learn about reaction favorability.